Hi, I'm Matt Samuel. I'm going to be discussing product-coproduct duality for double Schubert polynomials. So first we'll start with the symmetric group. The symmetric group S infinity is the group of all permutations of the positive integers fixing all but finitely many elements. We have special elements of the symmetric group Si, that's the adjacent transposition I plus 1. So that exchanges I and I plus 1. Sn, which it may be more familiar to you, is the subgroup of S infinity. It consists of all w's such that w of I equals I for all I greater than n. And we denote a statistic of an element w in S infinity, the length, by Lw, and that's the number of inversions of w as a permutation. So double Schubert polynomials, as in my other videos I'll mention, they represent Schubert classes in the torus equivariant cohomology of the complete flag variety of type A. They are polynomials in two infinite sets of variables, which we abbreviate as x and y, but they're xi and yi as I ranges over all positive integers. And the double Schubert polynomials form a basis for the polynomial ring zxy as a module over zy. So the double Schubert polynomials are indexed by the symmetric group S infinity, and we write them with a fracture S, they're Su of x and y for u in S infinity. And you can find a more detailed introduction in my Schubert seminar video. S infinity acts on the polynomial ring by permuting the indices of the x variables, and we can define these operators on the polynomial ring called divided difference operators. First, we recall that Si is the adjacent transposition, and we define the divided difference operator partial Si as 1 over xi minus xi plus 1 times 1 minus Si. So if you apply this to a polynomial, you take the polynomial, subtract what you get when you exchange xi and xi plus 1, and divide by the difference xi minus xi plus 1. And this will indeed always yield a polynomial. And these act very nicely on the double Schubert polynomials. We'll see why in a moment. If the length of usi is less than the length of u, then partial si applied to su of x and y gives you susi of x and y. If the length of usi is greater than the length of u, then partial si zeroes out the double Schubert polynomial su of x and y. So we can multiply the divided difference operators together and combine them to form composite divided difference operators partial u, so they're indexed by the symmetric group. And the relations on the divided difference operators are similar to those of the adjacent transpositions in the symmetric group. The only difference is that the divided difference operator squared is 0. So we define the double Schubert polynomials in terms of the divided difference operators. First, we let w0 of n be the top element of Sn plus 1. We define Sw0 of n of x and y as the product as I plus j ranges from 2 to n plus 1 of xi minus yj. And then for u in S infinity, define Su of xy to be partial u inverse w0 of n applied to Sw0 of n of x and y. And although it may appear that it does, this does not depend on the choice of n, so the indexing set is indeed S infinity. So since the double Schubert polynomials form a basis, they are structure constants cu vw of y that are polynomials in y that we may define by taking the product Su of xy times Sv of xy, and expanding this in terms of the basis, and the coefficient of Sw of xy is cu bw of y. Now, these coefficients have a known positivity property. They are polynomials in the differences yi plus 1 minus yi with non-negative integer coefficients, which was proved by Graham in 2001. I will be referring to this positivity property as Graham positivity. However, no positive formula is known, although some partial results are known. Now I'm going to introduce a new set of coefficients by introducing a third infinite set of variables z, which are very similar to x and y. They're just zi indexed by positive integers. We consider the mixed product su of xy times sv of xz. Now we can expand this in terms of the basis, and the coefficient of sw of xy is cubw of yz. This is the definition of cubw yz. We call this the Molev-Sagan coefficient. And I have a conjecture that these coefficients cubw of yz are polynomials in the differences yi minus cj with non-negative integer coefficients. I've tested this up to n equals 5, and I'm working with Kellen-Myers to try to test n equals 6. We've been running it for months, but we think the end is near. Although testing may not be necessary because it possibly can be proved with algebraic geometry. So I'll mention that the divided difference operators satisfy a product rule, otherwise known as the Leibniz formula, given by applying partial w to a product pq, and we expand this as a sum over all u and s infinity of partial u applied to p times partial uw applied to q. So this defines new operators depending on two permutations partial uw, called the skew divided difference operators. So the significance of the skew divided difference operators, besides being part of the Leibniz formula, is that for any polynomial p and a permutation u in s infinity, we can write the product p times su of xy as a sum over all w in s infinity. So we're expanding this in terms of the basis of double Schubert polynomials, and the coefficient of sw of xy is partial uw applied to p, but then we set x equal to y. So in particular, the Molev-Sagan coefficient cubw of xy is equal to partial uw applied to sv of xy. So let's discuss coproducts. Now, ordinary Schubert polynomials are what you get when you set the y variables to 0 in the double Schubert polynomials. So in 1998, Bergeron and Satilli considered the coproduct on ordinary Schubert polynomials, writing sw of x as the sum over all uv of s infinity of this coefficient dwuv of a times su of xa times sv of xb. Now here a and b are complementary sets of positive integers. And this coproduct, we're splitting the variables into the sets of indices a and b, and we're writing the full polynomial as a sum of products of these polynomials in the split indices. In particular, they are Schubert polynomials. So Bergeron and Satilli prove that these coproduct coefficients, dwuv of a, are themselves product coefficients. So they are structure constants of ordinary Schubert polynomials for some choice of u prime, v prime, and w prime, depending on u, v, w, and a. And in particular, they are non-negative, although no combinatorial proof is known, of course. So we will be generalizing this result with Molev-Sagan coefficients to double Schubert polynomials. A very well-known formula, I believe it was first found by MacDonald, and it's called the Cauchy formula. We express su of xy as a sum over u1 and u2 and s infinity, such that u1, u2 equals u, and the lengths add up. The length of u1 plus the length of u2 is equal to the length of u of this product, su2 of x times su1 inverse of negative y. Now there is a more general formula where we introduce another set of variables, a, specifically to write this coproduct, and the formula is exactly the same, except instead of su2 of x, it's the double Schubert polynomial su2 of x and a, times the double Schubert polynomial SU1 of a and y. If we set a to 0, this reduces to the ordinary Cauchy formula, and it's very easy to prove with divided difference operators. Now, we're going to define a sequence associated to a permutation U called its code. So the code of U is defined by defining code I of U to be the number of j greater than I, such that ui is greater than uj. So we're separating the inversions into indices, and we're counting the number of inversions that occur at each index. So a permutation is said to be dominant when the code is a partition, or in other words, it's non-increasing. So a property of dominant permutations is that U is dominant if and only if U inverse is dominant. So an example, we have the permutation U equals 642315. The code of U is 5311, and hence U is dominant. Now we're going to define subdominant permutations. We're going to let mu be a dominant permutation and let A be a set of positive integers. Then we will index A in increasing order, and just for a technicality, we'll assume without loss of generality that A is infinite. And then we define mu sub A, a dominant permutation related to mu, by saying that the ith index of the code of mu A inverse is equal to the ith index of the code of mu inverse. So we're taking the code of the inverse and we're picking out the indices that occur in A. So this operation or identification has the property that if A and B are complementary sets of positive integers, we can write the double Schubert polynomial S mu of x and y as a product S mu A of x and y A times S mu B of x and y B. This may appear very familiar. Knowing this and everything I've discussed up until now is all we need to introduce the product-coproduct duality theorem. So the theorem is we let W in S infinity be a permutation. We let mu be any dominant permutation such that the length of W mu is equal to the length of mu minus the length of W. Then we have this equation, SW of x and y is equal to the sum over certain u and v of cu mu a, v mu b, w mu of minus y minus z times su of xa and y times sv of xb and z. Notice the z comes out of nowhere. After summation it cancels out, but this is the coproduct for double Schubert polynomials mirroring the coproduct for ordinary Schubert polynomials, and we have the Molev-Sagan coefficients as the coproduct coefficients. So because of the known gram positivity of the Littlewood-Richardson coefficients of double Schubert polynomials, if we set z equal to y, this is gram positive, really gram negative. They're polynomials with non-negative coefficients in terms of yi minus yi plus 1. So even if we set y and z to 0, this is a new theorem for ordinary Schubert polynomials. And it's very easy to prove. So I'll take you through it. We write S mu of x and y as S mu a of x and y a times S mu b of x and y b. And we use the Cauchy formula, the generalized Cauchy formula, to expand this into a double summation over u and v of S u mu a of x and a times S v mu b of x and b. These are two new sets of variables, a and b, times SU inverse A, YA times SV inverse B, YB. So we can multiply the SU mu A of x and A times the SV mu B of x and B to obtain Molev-Sagan coefficients times SW mu of x and A. then we move the Molev-Sagan coefficients over to the right-hand side, and we flip the variables in the U inverse and V inverse double Schubert polynomials to get SU of minus YA and minus A times SV of minus YB and minus B. This is just an identity of double Schubert polynomials. And this is equal to, going back to the original generalized Cauchy formula, SW mu of X and A times SW minus Y and minus A. So we can extract from this the equation SW of minus Y and minus A is equal to CU mu A V mu B W mu of A and B times SU of minus YA and minus A times SV of minus YB and minus B. This is a sum over all appropriate UV. And with substitution, this is a proof of the product-coproduct duality theorem. So we can use product results to obtain coproduct results. So I've made 2 other videos about 2 other papers. So we have a formula for multiplying any double Schubert polynomial by a double Schubert polynomial corresponding to a dominant permutation. So the first part, for any U and W and S infinity and any dominant permutation mu, there's a positive formula for Cu mu W of Y and Z. In terms of Yi minus Cj, we have a specific formula that is also gram-positive when we set Z equal to Y. This is a consequence of the Pierre formula in one of my papers. We also have, for any V and W and S infinity and any dominant permutation mu, there's a positive formula for C mu VW of Y and Z in terms of Yi minus Cj. This is the dual Pierre formula. So we can apply this and apply the product-coproduct duality theorem to get the following corollary. So for any W and S infinity and any complementary sets of positive integers A and B, we have 2 formulas. For the first one, we set XB equal to Z. So that gives us a sum over all U, or all appropriate U, of Cu mu A, mu B, W mu of minus Y and minus C times SU of XA and Y. Now this is non-negative as a polynomial in Zi minus Yj because of the positivity of multiplying by a dominant permutation on the previous slide, and it's also gram-positive if we set Z equal to Y. The other way, if we set XA equal to Y, we get a sum of C mu A V mu B W mu of minus Y minus Z times SV of XB and Z. So this uses the dual Pierre formula, where the dominant permutation is the left index. So these coefficients are also non-negative in terms of Zi minus Yj. So for ordinary Schubert polynomials, we set Y and Z to 0. This gives us a positive formula for zeroing out any subset of the variables to obtain a sum of Schubert polynomials in the remaining variables with certain positive integer coefficients. So I have some other product results in the same paper that are actually consequences of the dominant permutation results. So let U, V, and S infinity and P greater than 0 be such that LUSI is greater than LU for all I less than P, and LVSI is greater than LV for all I greater than P. So U and V have separated descents in a certain direction. So then we have a positive formula for CUVWYZ. It's a polynomial in Yi minus Cj with non-negative integer coefficients that is also gram-positive when we set Z equal to Y. And in a different paper, we can flip U and V and also get a positive formula for the opposite separated descents case. So let's apply the duality theorem to use this to get coproducts. So the coproduct that we get here is when we split the indices into two intervals. So we're taking A to be 1 through P, and B to be P plus 1 to infinity. So we can split any double Schubert polynomial into a sum of double Schubert polynomials in x1 through xp and y times a double Schubert polynomial in xp plus 1 through the last x and z, and we multiply this by these coefficients that are positive in terms of zi minus yj, and they're also gram positive when we set z equal to y. So the proof is that if we let A be the interval 1p and B be the complement, then mu A and mu B have separated descents. So the formula on the previous slide applies. So the positivity result holds for the coproduct. Now this would be equivalent if y and z were the same, or if they were both 0. But if y is not equal to z, we have to go out of our way to get the opposite formula, where A is p plus 1 through infinity, and B is x1 through xp. So we get the positive coefficients. Again, they're separated descents, but in the opposite direction using the dual Pierre formula. So to any permutation u, we may associate a dominant permutation which we write as mu sub L of u, which we call the left dominant approximation. So we define this recursively. If u is dominant, set mu L of u equal to u. If u is not dominant, let I be the maximal index such that code I of u inverse is less than code I plus 1 of u inverse. Set mu L u to mu L si u. So this is the minimal dominant permutation over u in left weak order. So given this definition, it follows that for a permutation u, if we write the coproduct S mu L of u of x and y as the sum over u1 and u2 of su2 of x and a times su1 of a and y, then there is a term such that u2 equals u, and this is the smallest dominant permutation such that su of x and a occurs in this coproduct. So we've used products to get coproducts so far, but now we want to use coproducts to get products. So we identify coproduct coefficients that give us any product coefficient that we want. So first we define a dominant permutation for given u and v, mu L of u and v, to be the dominant permutation whose code is the sum of the codes of mu L of u and mu L of v. So given this definition, for any u vw in S infinity, cu vw of yz is 0, unless of Lw mu L uv inverse is equal to the length of mu L uv minus the length of w. In that case, cu vw minus y minus z is the coefficient of this product su mu L u inverse xa and y times sv mu L v inverse xb and z, and the expansion, the coproduct expansion of sw mu L uv inverse of x and y, and here we pick a such that mu L of uv sub a is equal to mu L of u, and mu L of uv sub b is equal to mu L of v. This is always possible to pick complementary subsets by definition that do this. So therefore, all product coefficients occur as easy to identify coproduct coefficients. So this product from coproduct theorem is easier to apply to ordinary Schubert polynomials. So we write the duality theorem for ordinary Schubert polynomials with zeros in place of y and z. So the equation is shown on the slide. Sw of x is equal to the sum over appropriate u and v, cu mu a, v mu b, w mu of 0, 0, su x and x sub a times sv of x sub b. So this is not the formula that Bergeron and Satilli found for the coproduct coefficients. Specifically, they identified the coproduct coefficients with these coefficients of the form C lambda W U cross V lambda 0, 0, where lambda has exactly one left descent. So it is very fruitful to combine these two characterizations. And we'll do that now. So we'll talk about left Grassmannian permutations. A permutation with exactly one left descent is said to be left Grassmannian. Schubert polynomials corresponding to left Grassmannian permutations are very rarely studied. The focus is mostly on right Grassmannian permutations, which give you symmetric polynomials that are called Schur polynomials. However, being able to multiply by a left Grassmannian Schubert polynomial is equivalent to having a little Richardson rule for Schubert polynomials. So I'll show you that now. So here's a breakdown of why Bergeron and Satilli's identification of the product with the coproduct coefficients work. So we suppose lambda is a left k Grassmannian permutation, so its left descent is sk. U is in the symmetric group sk, and v is in S infinity. And we define U cross K V to be the permutation obtained from U and V by shifting V up K elements and multiplying by U. So if we take the skew divided difference operator, partial lambda U cross K V lambda, this factorizes as a product of a divided difference operator, partial U cross KV, times a permutation lambda. So what does lambda do? Lambda moves for some set A, x sub A to x1 through xk, and it moves the complementary indices to xk plus 1 through infinity. And then this skew divided difference operator applies partial U to x1 through xk and partial V to xk plus 1 through infinity. So hence this is directly computing a coefficient in a coproduct. So this automatically gives you positivity for ordinary Schubert polynomials, but for double Schubert polynomials it does not, which is why we are focusing on ordinary Schubert polynomials at this time. So for each set of indices A and a positive integer n, there is a corresponding left Grassmannian permutation lambda n of A that sends x sub A to x1 through xn. So if we can characterize A as a union of m intervals, then lambda n of A for sufficiently large n has exactly m right descents. So m intervals, m right descents. So the number of descents of the left Grassmannian permutation determines how split up the coproduct can be, and this corresponds to how split up the descents can be in the corresponding products we can compute. We will discuss a hierarchy of descent separation given by this. So we define a condition for two permutations called m separated for some m. So we let U and V be permutations. We say that U and V are m separated if there exists disjoint closed intervals ai, bi, as I ranges from 1 to m, such that if P is strictly between ai and bi, then the length of USP is greater than the length of U, and if Q is not in the union of the closed intervals, then the length of VSQ is greater than the length of V. So we have this theorem. Suppose U and V are m separated and W is in S infinity. Then there exists a left k Grassmannian permutation lambda for sufficiently large k with m right descents. Notice this is the same m, such that CUVW 0, 0 is equal to this left Grassmannian coefficient CW mu L UV inverse lambda U mu L U inverse cross K V mu L V inverse times lambda of 0, 0. So it's a little bit icky, but being able to multiply by a left Grassmannian permutation with m right descents is equivalent to being able to multiply SU of x and SV of x, where u and v are m separated. So we don't even know how to compute the result when u and v are 1 separated. So let's discuss what 1 separated means. So a left Grassmannian permutation with exactly 1 right descent is also right Grassmannian. It's sometimes called bi-Grassmannian. And these are Grassmannian permutations that correspond to rectangular partitions. So if we had a formula for multiplying by a bi-Grassmannian permutation, then we can compute CUVW00 for all u and v that are 1 separated. So there exists P and Q such that the length of USI is greater than the length of U for all I strictly between P and Q, and the length of VSI is greater than the length of V for all I such that I is less than P or I greater than Q. So what this would allow us to do, for a very specific example, is it would allow us to multiply an arbitrary Schubert polynomial by an arbitrary Shor polynomial. This actually is also true conversely, since this is the bi-Grassmannian permutation. Schubert polynomial is a Shor polynomial. Being able to multiply an arbitrary Schubert polynomial by an arbitrary Shor polynomial lets you multiply 1 separated pairs of permutations. So in a sense, the bi-Grassmannian Shor polynomial is the hardest one to multiply by. So a formula for this may be on the horizon. Asaf and Bergeron working on a formula for multiplying a Schubert polynomial by a Shor polynomial. So back to double Schubert polynomials, just wanted to mention coefficient reduction. So note that in the product-coproduct duality formula, for any dominant permutation, we have the theorem that the coefficient of SU of XA and Y times SV of X, B, and Z is CU mu A, V mu B, W mu of minus Y minus Z. So we have freedom to choose the dominant permutation here. So if we consider any coefficient CU, VW of Y and Z, then we can pick A and B such that we have this identity. I'm not going to read the whole thing, but it identifies a product coefficient with a coproduct coefficient. This is actually the same as in the theorem previously. So we have this dominant permutation on top, mu L of U and V. Sometimes, and actually very often, we can replace this with a smaller dominant permutation to obtain a non-trivial reduction of the coefficient. And this is very useful when you're trying to test formulas where reduction allows you to rule out a case. So, thank you for watching. If you haven't already, you can subscribe to see more videos about double Schubert polynomials on Maths Schubert Calculus.